Hello community, so great that you are back. Chain of thought and a 30% performance increase? Is this really possible with some symbolic utility reasoning? Welcome to DecisionFlow, a new AI research implementation. Now this paper was something special because the first sentence was a little bit, let's have a look at this. Give me a scenario and a finite action set and a constraint. It prompts now the LLM to extract a semantic attribute with a relevance matrix where it elicits some numeric weights via a goal condition prompting, applies a specification threshold, epsilon to produce a filtered matrix where it computes here a utility function and selects here a maximum, thereby generating a faithful rational tracing influential attribute, active constraint, and contrastive comparison methodology. And I had a look at the sentence and I have to tell you, I did not understand a single word. So, I'm sorry, but I have to start at the beginning. So what is the core problem we are gonna address today? Core problem is the current or the contemporary LLMs lack a structured reasoning required here for high-stake decision-making, like in domain of finance or agriculture or healthcare, whatever you like. Because current models often generate a disconnected justification post hoc. So we want to have the decision process integrated in the active reasoning before any decision is made. So the proposed solution here by this research team, by DecisionFlow, is here a decision modeling framework that we put on top of our LLM. We do this by introducing here a latent utility-based reasoning layer that is specially trained within the LLMs, and this should enable us here a principle, interpretable, and constraint-aware decision-making process. Now, the second sentence was no help at all. No, because we begin now by constructing a semantically grounded representation of a decision space, and then by building on it, we infer here a latent utility function over the attribute space, enabling here the model to score each action while representing here the constraint and reasoning over the structured space. And I said, what the hell is going on? Who creates those spaces? What are the mathematical operations on these spaces? What is a representation on this particular space? What are allowed mathematical operation in this space? You have to give me something. This is just a beautiful wording, but where's the content? And I looked at figure 1, the overall framework of DecisionFlow, and suddenly it became so simple, you know? So, okay, we have some ideas here, and then we have an information extraction and structuring, a scoring, an attribute filtering, a goal identification, symbolic reasoning, and the transparent decision process with an explanation. So let's start and define the terms that we're gonna. You see, a utility theory simply models the decision making as a selection action that maximizes here an expected utility. And you say, hey, I know this. Yes, of course. Me too. I immediately thought about reward function to maximize here the future reward here for given a particular action, for selecting specific actions. Symbolic reasoning, manipulating of discrete, logical, or mathematical structure. Chain of thought prompting, you know this. Constraint satisfaction, action, attribute, matrix, the relevance matrix. This encode which attributes pertains to which actions. I said, who is going to define this? How you want to validate this? And I said, okay, is it not similar to the reward models in reinforcement learning? I mean, what is it? Now, if you look closer in reinforcement learning, the reward is typically explicit and observed from the environment. Now here in this DecisionFlow paper, the authors say our utility is latent, constructed via symbolic reasoning over a structured input. It is not observed, but interestingly inferred from the semantic structure of the scenario. And you might say, hey, this sounds absolutely mathematical precise, no? No, wait, it's get better. Temporal versus a static decision space. So reinforcement learning is fundamentally sequential. It deals with our trajectories over time, optimizing here the long-term cumulative reward with a maximum entropy optimization problem. Great, we know this. You have seen one of my last videos. Now, this new process of a decision flow is non-sequential because it is a single-shot decision, so it evaluates a set of discrete alternatives in a static context. So this means, regarding now the learning objective, in reinforcement, the policy is learned by interacting here with the environment using algorithms like the Q learning, the policy gradients, the actor critique model, the soft actor critique model, and you know all of this. But now this is different because now in DecisionFlow, no learning at all is performed. And this was the moment where I said, oh, wait a minute, okay. So instead, we just use here a prompt-based inference over the LLM to extract your utility function and make this here a one-shot optimization topic on the prompt. So you see, here you have in the first column reinforcement learning, and the second column the decision flow. And we have here a look at what is the reward, what is the utility, what is the decision type we take, multi-step compared to single step. The learning mechanism in RL is a gradient-based policy optimization, or a Q learning here. In DecisionFlow, it's a prompted symbolic inference run using the LLM, so completely different representation, implicit versus explicit symbolic decision structure. So you see, it's not at all anything to do with reinforcement learning. However, I mean, if we're talking about reinforcement learning and you insist that we have a look at this point, I have to tell you, both the reward and the utility serve now to score particular actions that are open to us. But reward, as you remember, is external, a time-stepped signal driving here the learning from the external environment, while the utility in this decision flow paper is an internal one-shot inference driving here an immediate choice. So it all depends here on the LLM. Great. Now, I ask at this particular point ChatGPT, and I already have the free version, I don't have the paid version, nothing, not even the $20 version. Just, I said, put in here the PDF and said, give me an example. Comes back and says, okay, so we have an action, there's a list of particular choices. Then we have the attributes. This is a table of attribute values for each action that the LLM generates of its knowledge. Then we have the weights, the corresponding W, the importance score for each action. We have the constraints, which actions survive here the filtering. So we say, hey, nothing more than $500 or nothing that we cannot do in 5 seconds or whatever you have constraints. And then once you have that, and we do this in JSON here, the host system, so the DecisionFlow orchestrator, takes over and builds now a utility function. Now, interesting, this utility function is here a very simple linear function. No? We compute the sums, we have just some matrix multiplication and some vector dot products, and we have then the maximum. And it tells me the LLM doesn't generate the Python code, it generates only the parameter and the structure. And the actual optimization step is straightforward numerical calculation on JSON. And this is what maybe here our ChatGPT got wrong, but more about this in about 2 minutes time. But it gave me a real nice example. I love this, you know. This is the way I work with ChatGPT. So a user, I have 2 coffee shops on my way. Shop A has a good coffee, 10 minutes walk, $3.50 per cup. B, average coffee, not really famous, 5 minutes walk, $2.75 per cup. Then you have your condition, then you have what you prefer. No? I care twice as much about the quality of the coffee compared to price, and distance half as much as price. Which should I pick and why? So this is the typical decision process. And now it runs with me here what ChatGPT understands from this particular paper. Yeah? And it says, okay, the orchestrator built this prompt and calls then the LLM. So build the prompt and said, hey, you are a decision modeling assistant given the scenarios. You have actions. This is the array of shop names and attributes. A map from each attribute name to a submap of action to value. Respond in a strict JSON. I'll give you the data now. Shop A, quality 8 out of 10. 10 minutes walk, 350. Shop B, 6 out of 10. You see, this is not what I said. I said good coffee, medium coffee. Now we have this translated here by the orchestrator into a numerical representation, and the other data are correct. So the LLM now returns a simple JSON. Huh? The actions are shop A or shop B. What action do I take? Do I go to shop A or B? The attributes are now multiple: the quality, the distance, and the price. And here we have the value for both categories. And then the orchestrator asks, hey, the user cares for the quality 2 times more than for the price, and for the distance here, half important as the price. Assign here the numeric weights accordingly, respond in JSON. And now the orchestrator was just a layer on top of the LLM, and now the LLM replies, okay, here's the JSON file with your data. So we have now defined the weights for our parameter, for the quality, for the price, and for the distance. Great. And now we filter. I have here no constraints, but you could say I don't want to spend more than $10, or I don't want to walk more than 20 minutes, or whatever you have as a constraint, additional constraint to the solution to the system, just put it in there, and then computes now the utility. At first we need here the data, then we need to generate a utility function, and then we have to calculate the utility function. So what we have? The orchestrator now runs a tiny piece of Python. But this is what ChatGPT tells us. This is not what's really happening. But never mind, let's stick with this interpretation of ChatGPT. We have to live with AI, so we have to understand what they do wrong and what they do right. Python code actions, okay? So we have 2 actions. Go to shop A or go to shop B. We have the attributes, we have the weights, everything I already showed you. So now the utilities. The utility function is here a simple function. We have now the weights of the quality times the attraction for this particular quality plus the weights for the price for the other attribute minus here, this you remember, minus 0.5 plus the distance. And the utilities are particular given here. So we calculate this. Action, attribute, weights, computed utilities, explain, imply in English now that we have the result. So the utility function itself gives us a result of 7.5, whatever it is, for shop A and 6.7, so less for shop B. So we calculated here, given here a particular reasoning pattern that is now mapped to a utility function that is defined by the LLM on itself, given our instruction. We have now the result. The best choice for me is now shop A, mentioning my given weights, my given preferences, and the price. And now the LLM answers because it knows now the utility function and it sees exactly which part of the utility function generates what. It can now say shop A scores 7.5 versus 6.75 for B because it has a higher coffee quality, carries double the weight of price, which more than offsets here the extra $0.75 and the extra 5-minute walk. This offers here the best trade-off between quality, cost, and distance. So in my understanding now, after having read ChatGPT and the paper, I thought, but you know what? This orchestrator is here simply an agent that has learned a function calling or a tool use or MCP, no? This is, if we just evolve here this layer of an LLM to an own agent with a tool use, it is so much easier, no? Then we have a simple Python environment. This is our tool to calculate now the inner products, the matrix multiplication, everything is fine. So what I thought, now listening to ChatGPT, I have here the main LLM, does the thinking. I have the layer that is here instructing here with the utility function how the LLM should perform and how the LLM should reason and how the LLM should build with what parameters the utility function. And then the LLM, the layer here, simply knows how to connect to a Python environment and calculates here the numerical calculation, comes back with the numerical result. And I thought, but this is nothing special, no? This is just here an agent with tool use that is now able, given here my verbal semantic expression of the complexity that I see. So the system can now build a C++ or a Python program, identify the factors, come up with a simple utility function, maybe include some risk factors or some preference options, and simply calculate this. And I get a result. But I had a feeling, no, this is not what I read in the paper, because I never read that there was now a function call or an API call to a different Python environment or whatever. So here's the paper. Please have a look yourself. This is fun. This is from University of Illinois here. This is from May 27. So this is from yesterday, 2025. And here it's beautifully. And, I love this sentence, no? Rather than predicting an answer directly from a prompt, no? Which all of the other LLM does, more or less, no? This new decision flow builds a semantically grounded decision space and infers a latent utility function to evaluate the trade-offs in a transparent, utility-driven manner. And now you understand why I thought, my goodness, I'm a complete idiot because I don't immediately understand what they are talking about. And you really have to read the paper to understand it. But let's look at the benchmark data. Before we look at the benchmark data, it is important that you understand a detail that we will find here in the final benchmark data. And this is here the study for it. Language model are alignable decision makers, application for the medical triage domain. Because there they come up with the definition, if we have now the same, no? We have a context, we have a question. Hey, we have a triage, so many people are lying in front of you. You as a doctor, on which patient you go first to help this patient? What is the alpha priority if you have 10 people lying in front of you in the hospital? So you have different attributes that you decide are your decision attributes, your decision maker attributes. They are called DMAs. And you can give high relevance or a low relevance here to particular attributes. So, for example, here, if you have a risk aversion, you do not like a risk at all, you can go with choice A. The company guarantees to deliver here the full amount in 7 days. Never mind what is the example. Or B, the company equally likely to deliver in 3 days or maybe in 11 days. It's your risk. So you can calculate now, and they did this, to my knowledge, for the first time here, different DMAs for a high and a low probability. So they decided here, how good is the system in understanding and calculating these different risk factors. So now we come back to our main study here, this decision flow, and here we have it. Now, looks innocent, but it's beautiful because we have a Llama 3.1 8B instruct model, and we have multiple really interesting data. So we have a zero shot, we have a chain of thought, our classical chain of thought, then we have a self-consistency check, and then we have final the new decision flow. Now, we do this here for the medical triage alignment. This is a data set that is published here, 2024. It has 62 scenarios over 6 different decision-making attributes, DMAs. And these DMAs you can run now on a high accuracy and a low accuracy. Well, I just showed you high or low preference. The results are quite different. Look at this. So just look at the first one. Zero shot gives us here with a high accuracy, so for the DMAs here, 87, chain of thought, a classical chain of thought, 88, self-consistency, 90, and then the new, famous, beautiful decision flow, 76. My goodness, what happened here? Just 76? Yeah, but somehow, interestingly, if they go here for the low DMA, situation changes, because from 17 with chain of thought, it now increases to 38, or self-consistency all 37.5. Now suddenly we are up to 52. So this is an interesting point of view. No? And then if we take the average, no, we are almost coming up to the same chain of thought or self-consistent 64. And they have here 64.4. So we have a 0.4 better performance, which is, yeah, okay. So then they have a second data set. And the second data set you see here. And you have an agriculture data set that contains 120 decision problems and enumerating combinations of available fruits. You are a farmer, you have a certain budget, and you want that the AI decide which fruits should you plant for the next year. And you say, hey, I'm located here, I have so much water, I have so much energy, I have so much workforce that can take care about this. So you have to maximize profit under uncertainty conditions. And if you run this, and this is a standardized test set, you see, hey, this is now interesting because now from 40 or 32 or 56, now we jump to 72, and this is a nice performance jump. And if you do this here also for stocks or for a financial market decision, you see quite similar, 56, 56, 72, 72. So you have about a 15 percentage point jump here in the performance if you calculate the average. Why? Let's have a look here at all the data, and we just had a look at the first, and now let's have a closer look at the last one. This is here GPT-4 Omni, so quite a powerful LLM, no? And you see here the zero shot already gives you here 88%. The self-consistency gives you 89%, and the decision flow gives you here 90%. So I wouldn't call it, hey, wow, great. No, this is on par. This is okay. Just if you go here for this low DMA structure, then you see, okay, there's a better performance. Now, why? Interestingly, I think it is in the numerical calculation. Yeah, and then we have here for the agriculture and for the stock. And you see, now it becomes really pronounced. Now, if you have 22 or 26%, we make a jump here to 64. And if you do the average and you calculate, here you have your 30% that I introduced you at the very beginning of this video. And that caught my attention. And I thought, how is this possible to have, compared to a chain of thought, 40% jump? So here we have the result. But you know what? This is now interesting because when we have computational reasoning patterns, or do we just have symbolic reasoning patterns here in this particular topic? Because then I would know immediately how to further optimize this and get more than 30% performance jump. Yeah, we have a GitHub repo, you see, just yesterday, just filling it up, published just yesterday, so maybe you have to wait some days for the full data. And they say, they tell us here, the final conclusion, yeah, up to 30%, this is all great and nice, but I'm interested in another question. Is DecisionFlow not just simple a tool using LLM? Because yes, we know when an LLM uses tool, and this is the whole point of MCPs and agent-to-agent protocols, when we use this, yes, we have so much powerful tools that we can use, like a Python environment, C++ coding environment. We can really calculate risk scenarios. We have ready to rock and roll GitHub repos where we can have the financial sensitivity analysis and whatever. No? Of course, if I have now a tool using LLM that can connect to all of these GitHub repos, use the code that was developed over years, of course I will improve my accuracy over a simple LLM that just uses a chain of thought. There's nothing new, no? So I thought closer here to the textbooks example the authors of DecisionFlow gave us. So they have a question. There's a bomb explosion, and this is the triage example. So you have a young woman, or you have to treat here a bomber pilot here, and the target bias is utilitarianism, and then you have here the chain of thought response. Yes, beautiful. Or you go now here with the DecisionFlow. So what you do, as I showed you, you need more data. Now you say patient A has severe fractures and high chance of bleeding out. Patient 2 has minor injuries, but a respiratory arrest. Patient 2 is more critical. So the system comes now from this verbal instruction and creates now kind of a numeric representation. And then we have probabilities, and the LLM generates here numerical probabilities. And then the system decides, the LLM, given its training and pre-training on effort, the knowledge, the inherent intrinsic knowledge, to come up with a simple objective calculation, a simple objective utility function. Then you can calculate the risk and the constraint, and you have calculated beautifully who should be treated first. However, if we go now for stock examples, and you have now here the historic price for a particular stock and for other stocks, and now you say, hey, listen, I want to invest $1,000 either on stock 1 or stock B, which actions should I take given this is the historic development? This was zero shot, or here you have the chain of thought prompt. This is now interesting because they say, okay, this is the first prompt, and then now you have enumerated the unknown factors that would affect my final decision. Yeah, but there are so many more environmental factors that are not available. Maybe the LLM has no idea that this particular company, and it is a public company with the stocks here, is sensitive to some market fluctuation in the Chinese market or in the American market or the European market sector. So all these unknown factors, yeah, the LLM can try to isolate it, but maybe it is, focusing on the wrong experiments or the wrong data, the wrong factors. And even if you then say, okay, I can also empirically estimate the possibility of an occurrence of each of the possible factors. So you have a LLM belief distribution over unknown factors. I would say we are now highly speculative here, given here very limited experience here of this particular LLM, if it's not a highly trained financial LLM or a financial multi-agent system. I would say, wow. But there's another point that is overshadowing all of this, because I also just run here some experiment with the new DeepSeek R1, the 0528, the new version from today. And I've given it a paper and I said, just to check, if my understanding is the same as the new R1 understanding. And R1 disagreed with me and said, no, you're not right. And R1 told me, hey, the DecisionFlow internalizes the mathematic. There is no function call, no API call, no agent or MCP call or whatever. The LLM does not offload the calculation. It treats them as a structured reasoning step via a transfer of a linguistic to a numerical translation. So if I say, hey, there's a threatening respiratory arrest, the LLM translates this here to this factor, so generated via a few-shot prompting, so no training, no fine-tuning, nothing. And a symbolic algebra, this is now interesting, where R1 tells us, hey, simple operations like weighted sums or comparison are handled autoregressively by the LLM. Now, this is a statement where I say, what? I mean, you remember, no? I mean, even here, if we go here to Open Router, no, is 9.9 or 9.11. Which one is larger? So if you just have an LLM without tool use, without access to Python or C++ or whatever, or to solvers, just the LLM going here with algebraic solution, I don't think this is a good idea. But okay, if this was the intention of the authors of DecisionFlow, that we have a symbolic algebra with weighted sums or handled autoregressively, this means predict the next token of the integer or the floating point number by the LLM. Yeah, it relies on LLM inherent ability to perform trivial arithmetic via token prediction. And yeah, it's really there in paragraph 5, and in-process execution calculation happen inside of the reasoning chain. And why this distinction matters, and R1 tells me, hey, in my understanding, the authors tell us they do not use tools. We only have a DecisionFlow that works with vanilla LLMs. No plugins, no APIs, no code interpreters needed, no solvers needed, no Python environments needed. Given that your LLM may be a small LLM that is not really trained for algorithmic operations, I would flag this here as a red flag. And I told this to R1, and R1 comes back and says, hey, you're absolutely right. And this is a critical insight that exposes here a fundamental tension in the DecisionFlow design, because this paper acknowledges this limitation, but employs a clever compromise that balances here the reliability with the reasoning transparency. So for R1 to find this, I have to say, impressive. So R1 goes on and says, the core problem is LLMs are notoriously bad at precise floating point arithmetic via next token prediction. It will yield hallucinated results. So I agree with R1, R1 agrees with me, beautiful. But the practical solution by the DecisionFlow team was now to avoid complex calculation. At first they do this by an aggressively sparsification. And they are setting here an epsilon threshold to prune here the low impact attributes. So whatever is now coming critically low, so you have to calculate carefully. They say, hey, this is under an epsilon, get rid of it, forget it. We just do, plus minus 10%, 20%, 30%, it's okay. So we do have an epsilon threshold that eliminates all not absolutely clear indicators. Plus, they use here the symbolic approximation, this linguistic quantifier, like, well, high, medium, low, and this maps here the numerical ranges. So this is a clever idea. I did not notice this. And then R1 tells me, that in their future path, in their outlook, how to further optimize here the decision flow, the authors tell us, yeah, it would be great here, further integration with neuro-symbolic architecture with a multi-agent collaboration to further boost the performance. So the translation is, then later include external solvers that handle here the optimization in a real Python environment, or we have here some particular solver, designated solver here to keep here the augmentation clean. Absolutely beautiful. It is different to the ChatGPT interpretation because ChatGPT interpreted that in the paper there's a Python environment. And I checked the paper and I even had a find in paper search, and there's not a single word about Python because maybe I overread it or whatever. I said I have to make sure. I went to the PDF, I went here completely, scanned it here for environment, Python environment, C++ environment, calculation. I found nothing. And then one came back and said, hey, key takeaway, DecisionFlow accepts now unreliable mathematics. And I said, what? As a tactical trade-off. And I said, what? In order to achieve a structured reasoning transparency, a constraint-based alignment, hey, I only have $50 to do this calculation, and some human auditable traces. And still wins 30% accuracy gains because in high-stakes domain, the qualitative structure is so much more important than the numerical precision. And R1 ends here, the new R1 ends here with the utility function is a reasoning scaffold, not a calculator. And for this insight, I love the new R1 system by DeepSeek. Such a delicate and beautifully equilibrium here of reasoning, understanding, and coming back and trying to help even here this stupid human, my person here, help it here to understand utility function is a reasoning scaffold, not a calculator. But of course, if we would add here the tool used for Python environments, we could even further improve with a numerical calculation for more critical decision when it is not absolutely clear. Alpha is priority, beta is secondary. Because if both are, 49% to 51%, then it will become really difficult to make it a decision. In the simple cases, okay, we go here with DecisionFlow. We have an absolute threshold that kills off everything below a certain threshold, and we go for the major decision blocks. But even this helps us over a chain of thought. So this 30% accuracy gain is there for a very particular number of cases that are also in these benchmark cases that the authors tell us. So absolutely fascinating. If you I start with a paper where I say, I don't understand anything, help me. And I look at ChatGPT and I look at R1 and I see how the evolution from a free ChatGPT model that is now, several weeks old, and the brand new R1 that is just 1 day old, there's really a difference. So you have to be careful which model you use for which particular case. If you just go for coding or web development, you know which model to use. But if you go here for explanation, if you go for understanding, for causal reasoning, for logic, you could give here your, level of experience here to R1, and it will help here with the designed explanation particular to my knowledge level or your knowledge level. So I think this is great. I found R1 here, this particular real-world use case, helpful to explain here everything. Yes, I have to notice that the complete research here by DecisionFlow is here supported here by the DARPA program. Beautiful. And the views contained here are not the official views by the US government. It was just here financed by the US government. Interesting, the DARPA program, what they are currently exploring here. But okay, so here we have it. A very strange paper with a lot of insights, with a beautiful testing here of the latest R1 model. See here the limitations of the free ChatGPT version here. and gain some insights how to optimize further with a chain of thought that's now so clear how we can get an improvement of up to 30% in our causal reasoning. I hope you enjoyed it. If you like this kind of videos, why not subscribe, and I see you in my next one.